Welcome to today's deep dive. We have a really specific mission curated just for you today.
Yeah, we are getting into some wild territory, the absolute extremes of chemistry.
Right. So we've been looking through this huge stack of sources, astrophysics papers, industrial chemistry, biological studies, and it all centers around one single thing, atomic number 9 on the periodic table.
Fluorine.
Exactly, fluorine. And, just to set the stage here, if you think about the elements that make up our world, oxygen is kind of like, a cozy campfire.
That's a good way to put it, yeah.
Right, like it sustains life, it gives us energy, it keeps the whole biological engine running. But if oxygen is that warm campfire, fluorine is, it's a corrosive, totally uncontainable flamethrower.
It really is. It's chemistry pushed to maximum aggression. Honestly, it acts as the ultimate chemical predator.
And the reason this matters to you, listening right now, is that you actually interact with this element every single day.
Oh, constantly. I mean, it's in the toothpaste you used this morning, it's literally fundamental to the microchips inside the device you're listening to us on right now.
The nonstick pan you might use for dinner later.
Exactly. Yet, despite being everywhere in our daily routines, it remains one of the most dangerous, hyperreactive substances in the known universe.
Which is crazy to think about. So, to understand how this deadly pale yellow gas ends up sitting safely in our medicine cabinets, we kind of have to start at the beginning.
Deep space.
Right, its cosmic origins. And reading through the astrophysics papers, I was honestly struck by how rare fluorine actually is in the universe.
It's surprisingly rare. It's a total latecomer to the cosmic party.
Yeah, it definitely doesn't feel like a foundational building block the way, carbon or oxygen does.
No, not at all. It requires these highly specialized, incredibly violent stellar processes just to form.
Like what kind of processes?
We're talking about environments like asymptotic giant branch stars.
Okay, meaning what exactly?
Basically, massive dying stars that are violently shedding their outer layers. Or Wolf-Rayet stars, which burn so hot they blow off these gale-force stellar winds.
Wow.
Yeah, and it's also forged during supernovae. The intense neutrino interactions of a collapsing star create enough pressure to actually smash particles together into fluorine.
Okay, but wait, I'm struggling to square that.
Yeah.
Because if it requires a literal dying star or a supernova just to be created, and those same explosive nuclear fires can easily destroy it, how did we end up with enough of it on Earth to use it?
That is the million-dollar question.
Right, like it seems like it should have just burned itself out billions of years ago before it ever reached a planet.
The secret to its survival is entirely its chemical personality. Fluorine survived on Earth precisely because it is so incredibly aggressive.
Okay, how does being aggressive help it survive?
In chemistry, we measure this through a concept called electronegativity. And fluorine is, hands down, the most electronegative element known to science.
Okay, for the non-chemists among us, including me, we need to break down what that actually means on a molecular level.
Sure. So electronegativity is basically an atom's ability to attract and hold on to electrons. And fluorine's atomic structure makes it, an uncompromising thief.
The thief.
Exactly. Its nucleus is relatively small, meaning the positive charge of its protons is very close to the outer edge of the atom.
Okay, so the distance is short.
Right. And that proximity creates this massive, almost obsessive gravitational pull, chemically speaking, on any nearby electrons.
So out in the cosmos, it might be fragile when exposed to, nuclear fusion.
Yes, but once it cools down and encounters other elements in a planetary dust cloud, it becomes the strongest oxidizer in existence.
So it survives by just latching onto anything it can find and absolutely refusing to let go.
Exactly. It aggressively strips electrons from other atoms. I mean, it reacts with metals, it tears apart non-metals, it destroys glass.
Wait, it destroys glass?
Oh, yeah. And it reacts explosively with water. Under the right conditions, it even forces noble gases to bond with it.
And noble gases like krypton and xenon? They're famous for their complete chemical stability, right? They never react with anything.
Usually no, but fluorine forces them to. That's how strong it is.
But if free fluorine gas is that reactive, it obviously couldn't just, float around in Earth's early atmosphere.
No, definitely not.
It would have just immediately attacked the nearest mountain or the ocean or completely reacted with the air itself.
Which is exactly why Earth essentially put this apex predator in planetary quarantine.
Planetary quarantine. I love that phrasing from the sources.
It's accurate. It bound itself into the Earth's crust. It basically locked itself away in minerals like fluorite, cryolite, and fluorapatite.
One of the papers described it as a crystalline straitjacket.
That's exactly what it is. By forming these minerals, the fluorine atoms pull the electrons they desperately want from elements like calcium.
And once their electron hunger is satisfied, they just sort of lock in.
Yep, they lock into a rigid, stable lattice. So deep in the crust, it's perfectly safe and neutralized. It influences groundwater and volcanic gases, but it isn't roaming free.
And that mineral form is how biology actually interacts with it, right?
Yes. And biologically, fluorine exists on this really fascinating razor-thin boundary between protection and poisoning.
Right, because unlike carbon or oxygen, our bodies don't use fluorine to run our core machinery.
No, it isn't found in our DNA, it isn't in our proteins, and it's not in ATP adenosine triphosphate, which is basically the fundamental molecular battery that gives our cells energy.
But it does interact with our biology. I
Yeah.
mean, anyone who has looked at a tube of toothpaste knows that.
Oh, for sure. The trace amounts of fluoride, which is just the negatively charged ion form of fluorine, actually swap places with weaker compounds in our teeth.
To create fluorapatite.
Exactly, which is this harder, way more decay-resistant armor for your tooth enamel.
So it protects the teeth. But, and this is a big but, if you cross that boundary of exposure, the effects are pretty devastating.
Extremely. High levels of fluoride cause fluorosis, where that same mineralization process just goes completely haywire.
Leading to severe bone damage.
Right. And at extreme exposures, it causes systemic toxicity and major neurological disruptions.
Which brings us to a really fascinating turning point in the research.
The extraction.
Yes. We have this deadly element, safely locked in a rock, capable of causing severe biological damage. But to harness it for industrial use, humanity had to figure out how to break it out of that crystalline straitjacket.
And the tool we use to do that is hydrofluoric acid, or HF.
Which is terrifying,
Yeah.
because to extract elemental fluorine, you can't just melt the rock. Or
No, you have to process those minerals using HF, and HF is widely considered one of the most dangerous, feared industrial chemicals on the planet.
Honestly, the medical notes in our research regarding hydrofluoric acid exposure, they're genuinely terrifying to read.
They really are.
Yeah.
Because most strong acids, like sulfuric or hydrochloric acid, they're highly charged.
Right, so if you spill them on yourself, they react immediately with the surface of your skin. You get these painful, visible burns right away.
Exactly. But hydrofluoric acid operates completely differently. It operates almost like a ghost.
A ghost.
Yeah, because the bond between the hydrogen and the fluorine in HF is incredibly strong, so the molecule doesn't immediately break apart into reactive ions when it touches you.
It just remains this small, neutrally charged molecule.
Right, which allows it to slip right through the lipid bilayer of human skin without burning the surface at all. It doesn't even trigger your nerve endings immediately.
So it just penetrates deep into the tissue, completely undetected.
Until it hits the watery environment of your bloodstream and your bones.
Oh, man.
And there, it encounters calcium and magnesium. And because fluorine's attraction to calcium is so overwhelming, it finally breaks away from the hydrogen.
And forms insoluble calcium fluoride.
Yes.
Yeah.
It essentially precipitates the calcium right out of your blood and
It
bones.
just steals it.
Steals it completely. And this catastrophic drop in calcium disrupts the electrical signaling in your entire body. An exposure the size of the palm of your hand can lead to rapid cardiac arrest.
That is insane. Knowing how dangerous this is, knowing it requires a chemical capable of bypassing human skin to steal calcium from our bones, humanity still went after it.
We did. We actively hunted this element down to build modern civilization.
Which is wild. The industrial chemistry papers highlight this concept called a Tier 2 level of dependency.
Right. So a Tier 1 civilization relies on foundational resources, steel, water, agriculture, basic electricity. We can survive and have cities without fluorine.
But a Tier 2 civilization involves high-tech systems.
Exactly. The complex, miniaturized, highly efficient tech that makes the modern world modern. Without fluorine, maintaining a Tier 2 civilization becomes incredibly difficult, if not flat out impossible.
We basically took the most stubborn, aggressive element and forced it to do the heavy lifting for our most advanced technology.
We weaponized chemistry in a way.
Literally. Reading through the historical sources, it's clear that the modern unleashing of fluorine is directly tied to the dawn of the nuclear era.
Oh, absolutely. To enrich uranium for nuclear fuel and weapons, scientists face this massive physical problem. Uranium is a really dense heavy metal.
And to separate the fissile uranium-235 from the heavier uranium-238, you have to spin it in a centrifuge.
But you can't spin a solid block of metal in a centrifuge to separate its isotopes. you need to turn it into a gas.
And fluorine was the key to making a uranium gas,
Yes. They created uranium hexafluoride, or UF6.
which goes back to the electronegativity we talked about earlier.
Right. The extreme electronegativity of fluorine allows it to bond strongly to the uranium, volatilizing it into a gas at relatively low temperatures.
It's brilliant.
It is. Plus, fluorine only has one stable natural isotope. This is a highly critical detail.
Because all fluorine atoms weigh exactly the same.
Exactly. So any tiny difference in the weight of a UF6 molecule is purely due to the uranium isotope inside it.
Which allowed them to separate the uranium precisely.
Yep. Without fluorine, the nuclear age as we know it simply would not exist.
And that realization that fluorine bonds so aggressively to other things that the resulting molecules are incredibly tough, that led us straight to organic chemistry.
Specifically, the carbon-fluorine bond.
Right. When fluorine, with its massive electron hunger, bonds with carbon, it creates one of the strongest single bonds known in chemistry.
And humanity looked at that unbreakable bond and realized its massive potential for material science.
The mechanics of it are actually brilliant. I mean, we used it to make Teflon, the nonstick coating on our frying pans.
It's quite the leap, isn't it?
It really is. You take this hyperreactive element that wants to destroy everything, and you force it to bond with a carbon chain.
And because the fluorine atoms are so bulky and they're holding onto their electrons so tightly, they form this dense, impenetrable shield around the carbon spine.
It functions almost like a microscopic source field.
That's a great analogy. The fluorine atoms are so satisfied and so tightly packed that they just repel the electrons of anything that comes near them.
Water, oil, eggs, chemical solvents, nothing can get close enough to interact with the carbon chain.
It's a brilliant manipulation of extreme chemistry. We used fluorine's uncompromising nature as a tool for transformation just through overwhelming chemical pressure.
And the applications go way beyond cooking. I mean, these fluoropolymers resist heat, corrosion, and chemical attacks.
Making them absolutely essential for aerospace engineering.
Right, like O-rings, fuel lines, wire insulation, and satellites. They all rely on that impenetrable carbon-fluorine shield to survive the extremes of space.
We also see this deep dependency in the semiconductor industry.
Oh, this part of the research was fascinating.
Right. To make a microchip, engineers have to etch microscopic pathways into silicon wafers. But you can't just pour liquid acid over a microscopic grid.
Because capillary reaction would ruin the precision, and the liquid would just wash away the delicate structure.
Exactly. You need a gas.
And the sources detail how they use fluorine gas in a plasma state for this.
They put a fluorinated gas into a chamber and blast it with electromagnetic energy until the electrons are stripped away. This creates a plasma, which is basically a highly reactive ionic soup.
And then they use magnetic fields to direct this plasma to bite into the silicon.
With absolute atomic level precision. It is aggressive enough to carve the pathways, but controllable enough that it doesn't destroy the surrounding chip.
So the device you, our listener, are holding right now, it functions because of the aggressive, corrosive power of plasma state fluorine.
It's everywhere. We even rely on it inside our own bodies. A significant percentage of modern pharmaceuticals contain fluorinated molecules.
Just by adding a single fluorine atom to a specific spot on a drug molecule, chemists can fundamentally alter its behavior.
Because the liver is incredibly good at breaking down foreign chemicals using enzymes. But if a chemist puts that unbreakable carbon-fluorine bond right where the liver enzyme usually attacks the drug,
It acts like a shield.
exactly. It prevents the drug from being metabolized too quickly, ensuring it survives long enough in your bloodstream to effectively target the disease.
It's wild. We took a pale yellow gas that produces violent flashes and corrosive smoke in its natural reactions, and we tamed it to heal us, connect us, and power our cities.
It really demonstrates our deep fascination with mastering highly reactive forces.
But, of course, mastering a relentless predator comes with consequences.
The bill is definitely coming due.
Right. The very chemical strength that makes fluorine so incredibly useful, that unbreakable carbon-fluorine bond, has created a pervasive environmental crisis.
Because the strength of that bond doesn't just disappear when a product reaches the end of its life cycle.
Normally in nature, materials break down because water, sunlight, or bacteria have the energy to break their chemical bonds.
But natural forces do not have the energy to break the carbon-fluorine shield.
Which brings us to PFAS, per- and polyfluoroalkyl substances.
Widely known as forever chemicals.
Because we engineer these compounds to resist breaking down under heat, water, or chemical attack, they persist almost indefinitely in the environment.
They don't degrade, they just accumulate. They wash off our nonstick pans, our waterproof jackets, our industrial sites, and they settle into the soil and the groundwater.
And from there, they enter the food chain and eventually our bodies.
It's a huge issue. We demanded materials that would never corrode, never stick, and never break down. Nature provided the carbon-fluorine bond, and we exploited it on a massive scale.
And now we have materials that literally last forever in our water supply.
It highlights this recurring dilemma in industrial chemistry. Fluorine gave humanity enormous leverage to solve the technological bottlenecks of the 20th century.
But we applied it in ways that were beyond our ability to manage safely in the long term.
And PFAS is not the first time we've seen this with fluorine.
Right. The sources outline the whole history of CFCs, chlorofluorocarbons.
Yeah. Fluorine-based refrigerants revolutionized how we keep food cold and air condition our homes because they were chemically inert and safe to use inside a house.
But when they drifted up into the upper atmosphere, the intense ultraviolet radiation from the sun finally had enough energy to break those bonds.
Releasing free chlorine and fluorine radicals that systematically dismantled the ozone layer.
At least until scientists realized what was happening and global bans were enacted.
True, but we also have to acknowledge the immediate human costs of utilizing this element. Industrial accidents involving fluorine are, well, they're rarely minor.
Because of its extreme toxicity and corrosiveness. If a containment system at a chemical plant fails, the resulting release is highly lethal.
It poses an immense, constant challenge for the engineers tasked with keeping it caged.
It's really the embodiment of the danger of utilizing extreme power.
Exactly. Most elements in the periodic table compromise, you know. They share electrons fairly easily, and their bonds can be rearranged with moderate energy.
But fluorine does not compromise.
It seeks electrons with relentless intensity. The tools we build from it are incredibly powerful, but completely unforgiving of miscalculation or short-sightedness.
So what this leaves us with is a profound realization about the duality of progress. We're walking around, brushing our teeth, using our phones, completely oblivious to this invisible, highly aggressive chemical architecture operating behind the scenes.
But fluorine's story isn't purely about toxic gas and environmental contamination. I mean, its chemistry fundamentally protects us, too.
It stabilizes the critical medicines that treat chronic diseases. It enables the high-tech semiconductor networks that run global communications. And it provided the materials that allow us to explore space.
Hydrogen began the universe. Carbon built the complex scaffolding of biology. Oxygen sustained the energy required for life to thrive.
But fluorine pushed chemistry to its absolute extremity.
It represents the outermost limits of what atoms can do to one another.
So for you listening, the next time you use a nonstick pan to make breakfast or take a fluorinated medicine or, just brush your teeth before bed, take a second to recognize what you are interacting with.
You are holding a tamed cosmic predator.
An element born in the explosive death of massive stars, one so uncompromising that the Earth itself had to lock it away in a crystalline cage just to survive its presence.
And you are holding a testament to human ingenuity, our ability to extract that danger, study it, and mold it into a force that drives advanced civilization.
But it does leave us with a lingering thought to mull over when this deep dive ends. We unleashed this corrosive, uncontainable flamethrower to force technological leaps, and now we are navigating an environment seeded with forever chemicals that just refuse to fade away.
It's a heavy thought.
As we continue to engineer new, seemingly indestructible synthetic materials to solve today's problems, are we still just cleverly caging the beast? Or have we permanently altered the chemical makeup of our planet in a way that Earth's natural mineral quarantine can never fix? Thanks for joining us on this deep dive. We'll catch you on the next one.